It's really a great pleasure to introduce Andrei, who really needs no introduction to this community. Andrei is one of the leading high-energy astrophysics theorists that works in the world today. He's written many deep, penetrating papers. All of them are worth reading. He's concentrated mostly on, I counted 5 topics. So one topic is obviously gamma ray bursts, which he's going to talk about today, but also magnetars, radiant gamma ray pulsars, accretion disks, and dynamics of stars in the galactic center. So without further ado, Andrei, could you please tell us something interesting about gamma ray bursts?
Thank you for the introduction. Am I allowed to share slides now?
Yes, please go ahead.
Okay. Okay, is it good?
Yeah,
you can see it.
That's good.
Okay. Okay, so let me start then. Well, you see a ridiculous list of topics. So almost certain I will fail to talk about all this stuff. But anyway, today I decided to try the impossible. So let's see how it works out. So the idea is to talk about physics that may be responsible, that may be behind particle acceleration that we so like, and in particular in GRBs. Okay, and so I want to start with this cartoon. And every GRB talk basically starts with this cartoon. Almost from a student or someone old in the field, they usually start showing this kind of cartoon. There are nice colors usually, and there is something flowing out, and you can see gamma rays and X-rays and from GRB and afterglow. So it all came from 1990s, which was kind of heroic time of cooking phenomenological models. So what you would call GRB theory at the time, and many people still call it now, 20, 30 years later, is like trying to come up with a picture and say something plausible and communicate it with the observers, because there was there was a flood of observational data, discovery after discovery, and observers desperately needed some picture to try to use it to interpret data. And so this is the summary of this picture. There is a jet which has to be ultra-relativistic. We know that from opacity considerations, otherwise the emission would not escape that we see on the 1 second time scale. And there are internal shocks that will picture it as sources of the prompt gamma ray emission, the MEV, mainly MEV emission. And then there was external shock that is responsible for the broadband afterglow emission. So a blast wave driven by the explosion into an ambient medium. And so here's the paradise for observers, because theorists are offering them a prescription. So you just inject particles with this spectrum, right? This is a spectrum. There's maybe hundreds or maybe 1,000 papers written discussing this kind of spectrum of accelerated particles. It starts at some energy, which has to be high, otherwise it does not produce neutron emission at the right frequency. So it's very much ultra-relativistic energy of electrons. And then there is a power law starting from that low energy cutoff. And the two usual parameters are epsilon E and epsilon B that we know and love. Epsilon E is what fraction of whatever carries, whatever is the energy, the fraction of the energy reservoir, let's say shock energy, that is channeled into this thermal electron distribution. And then epsilon B, which parameterizes the strength of the magnetic field. So, particle distribution of magnetic field, that's it, you can calculate the radiation that comes out. And you can do this in time, plotting it with, for example, self-similar blast wave model length and Mackey. All right, so of course, the question that immediately should come to minds of many people is actually, are particles will accelerate in shocks? And the answer, well, the assumed answer was yes, because you think that supernova shocks accelerate particles. But really, the animal that we're dealing with in this problem is the collisionless shock, right? Which is known in plasma physics since the 60s. And one of the very first papers to just import this plasma physics that was known before and adapt it to the GRB collisionless shock was this paper by Misha Medvedev, who was trained as plasma physicist in Ivy League. And so they basically said, well, I mean, shock has to be mediated somehow. We talk about collisionless shock. And so the picture of collisionless shocks is that as two flows start to penetrate each other, let's say the ejectors start to penetrate into ambient plasma, they form a two-stream configuration, which is unstable to Weibel instability in particular, which is sketched here from paper by Moiseev and Zagdeev in 1963. And this turbulence means fields, electromagnetic fields that can scatter the particles and thus create effective finite free path for particles. And that's how the shock would be mediated. So you can see this filamentation instability in the plot from Moiseev and Zagdeev when you have perturbed magnetic field and it's self-consistent with runaway amplification of this field by the streams of particles, by currents that field generates by focusing particles. So the field here deflects particle this way and particle the field here this way, and the opposite particle opposite direction. So there is a current, local current thread growing, which feedbacks positively on the field. And that's how Weibel instability works. Okay, it develops roughly on the plasma timescale. Okay, so shocks can be mediated, no problem. Collisionless shocks do exist. Next question, are particles accelerated in shocks? Yes, so this is the paper by Anatoly Spitkovsky. There are many other papers, but this is the first, I think, really convincing paper that showed how a Weibel-mediated shock, in this case for pure plasma, generates an non-thermal tail. So you can see the particle distribution. This is quasi-thermal, Maxwellian, and then there is a parallel tail. It doesn't look like, it's not quite like what people were picturing in afterglow theory, right? It's not quite this, this spectrum. So there is a pronounced Maxwellian component. About 10% of energy goes to non-thermal tail, which is not surprising. Of course, these kind of tails are known in solar plasma as well. Okay, but this is relativistic shock. I believe in this case it was gamma shock 15 or something. And you see here particle trajectories, how they gain energy, and how they gain energy by bouncing between upstream and downstream. And these curves are the magnetic, show the magnetic energy density. You see how it is amplified at the shock. This is the scattering magnetic fields that help the particles, you know, do bounces back and forth. Okay, so particles are accelerated in shocks. Great. Then the next question, how far in energy they can be accelerated? How fast is the acceleration? And so in this series, by the way, in these talks, we often see this kind of formula when we scale the acceleration time scale with the Larmor time scale. And it would be, let's say, 10 times longer Larmor time scale. So for shocks, it's not, it's kind of wrong logic. So Larmor timescale in the absence of background field is determined by the fluctuating fields themselves, but they fluctuate on the scale lambda, the coherent scale lambda, which is much smaller than the Larmor radius. And so the field scatter particles, and this is well-known fact by now, scatter particles on the time scale that goes as Larmor radius squared divided by this coherent scale, which is smaller than Larmor radius divided by c. So the scattering time is much, much greater than Larmor radius. And importantly, it goes as energy squared because Larmor radius goes as energy of the particles squared. So if you reverse it, you can kind of guess immediately that energy goes to square root of time. And that's what was seen, like as you keep evolving particle and cell simulation, this kinetic simulation that Anatoly Spitkovsky did, and then here I'm showing a snapshot from Lorenzo Cironi work in 2013. So you can see color is magnetic energy density. You see these magnetic filaments, and you see this shock kind of structure, the transition through magnetic energy glasses. And so particles do scatter back and forth, but as the energy grows, they do this in longer and longer time scale. And as you keep evolving the simulation, the cutoff of the energy spectrum of particles moves with time as time to the 1/2. So when you compare this growth of gamma law with how much time you've got for the blast during the explosion expansion, you find that particles can be accelerated roughly to PeV energies, which is pretty good. But it's not, of course, ultra high energy cosmic rays. It is not enough time for that. Okay, and that's well known by now. There are several works after that, and these are first principle plasma simulations done in 2D and 3D. I don't see how this conclusion can be changed very much. Another interesting finding, which of course was anticipated at least from the beginning of the 90s, but for example, Bigelman and Kerr 1990, but I'm sure there are earlier papers. People kind of anticipated that if you have a background magnetic field, then which is strong enough, then the shock will not be Weibel instability mediated, and the particles will not be accelerated by Fermi mechanism. Simply because when you have sufficiently strong field, particles begin to gyrate behind the shock and get advected by the magnetic field behind the shock. Of course, here we're talking about so-called superluminal shocks. Okay, so these are shocks that have magnetic field transverse enough in the downstream frame, so that effectively it's perpendicular to the shock normal, and this perpendicular magnetic field lines, particles gyrate about these field lines, and as they keep moving downstream, they drag particles with them away from the shock, and they do this faster than this scattering process due to actually instability is not even quite working, Weibel instability. The particles are simply advected. They heat it up to Maxwellian distribution, and then they advected away from the shock. That was anticipated, but it was also demonstrated with simulations by now. For example, so Martin Limon also has several papers about this. Ilya Plotnikov, both analytically and now numerically, we know that magnetic field kills transverse shocks. Now, any relativistic shock is basically transverse, right? Because we are looking at the magnetic field in the downstream frame that is moving toward the upstream with high Lorentz factor. And so whatever orientation of the initial magnetic field is, from that frame, from the blast frame, it looks transverse just because of angle transformation. And this series of plots shows magnetic energy density, but in addition to this first panel that I showed before, sigma equal to 0. Sigma is the magnetization parameter, 0 background magnetic field. Sigma is defined here. It's the initial upstream magnetic field ahead of the shock, normalized to the mass density, rest mass density of the plasma. So when sigma is 0, you have healthy Weibel instability. And when sigma drops below 3 times 10 to the minus 5 for electron ion shock, shown here, then that's it. Weibel instability is suppressed, particle acceleration is suppressed, and at sigma 10 to the minus 4, you have quasi-Maxwellian distribution. So this figure shows the results of peak simulations for a shock that moves with relative Lorentz factor between downstream and upstream is 15, and different colors correspond to different initial magnetization of the medium ahead of the shock. And you can see sigma 0, good no thermal tail, sigma 3 times 10 to the minus 5, yeah, you see a limit already. It starts to affect it. 10 to the minus 4, that's it. 10 minus 3, it's gone completely. So the bottom line here is that if you have a little bit of magnetization, you quench Fermi acceleration of particles. And again, in plasma physics community is established, a well-known fact. In GRB community, and it's the reason why I'm going through that, because it's supposed to be a little introductory. Surprisingly, still not known by many people, I think. Okay. Now, what is expected sigma? If you deal with interstellar medium, then sigma can be really low. If you take ISM with typical magnetic field, sigma would be micro-Gauss magnetic field, you would have 10 to the minus 9 for sigma. So no problem. You have Fermi acceleration, you'll get PV particles. With one caveat, I'll come to that at the end of my talk. It's for electron ion shocks only. And then if you deal with Wolf-Rayet progenitor wind as external medium, then if the wind of the progenitor, way before the explosion, 1 year before the explosion, this wind from the Wolf-Rayet star into which the GRB explodes, this wind, if you assume a equipartition magnetic field, a kind of maximum, so you would get something like 10 to the minus 5, 10 to the minus 6 for sigma. Still okay. So external shocks can accelerate particles. But what about internal shocks? For internal shocks, basically there is no way for Fermi acceleration to work, I think. And it's true also for mild relativistic shocks. The simulations have been done for mild relativistic gamma as well. And the argument, of course, applies to that still quite well. Why you suppress it?
What's your definition of mildly?
Gamma of a few. Of course, if you want internal shocks to be efficient, you really want high gamma. Actually, you wouldn't get away with gamma of like 1.2 or something. But I think even if you have gamma of 1.5, you have still the same conclusion. You have a critical sigma above which you quench the particle acceleration.
But when gamma is 1.5, that not all the magnetic fields are transferred.
Sorry, say it again.
When gamma is 1.5, you still can have significant angle for the what do you call it?
Yes, that's right. Yeah. So it's not exactly transverse, because I'm saying here it's transverse field. And how do you know with transverse if the field is not?
If you have internal shocks with a Lorentz factor of 1.5, you can estimate that the magnetic field will be in all directions. So there will be regions where you do accelerate.
Yes, that's true. However, if we talk about jets that carry magnetic fields, this magnetic field will most exactly transfers to the wave speed. Sorry, to the jet speed.
With that. This is correct.
Yeah, because magnetic field is frozen.
Yeah, I agree.
Into the flow. But for others, I know you know that. But for other people, just in case if you miss this simple argument that if you have magnetic field frozen into an expanding flow, its radial component, toroidal component goes as 1 over r squared, and toroidal component, transverse component goes as 1 over r. So if you let it expand, it expands by many orders of magnitude, it becomes transverse. Okay, so I think it was kind of red herring, and I think many people would agree with me that this idea that we have to have non-thermal source from, and it has to be synchrone emission from internal shocks in the jet, it's been repeated many times, but over the years. But it doesn't make it valid just by repeating it. In fact, it was not even required by or preferred by the data. I don't want to go into detailed discussion because I have other things to discuss. But basically, if you look at, if you try to fit the data with this model, it actually doesn't give you a good fit for many GRBs. And also, it doesn't quite explain the preferred position of the MEV peak. But this is a long discussion which came up several times at GRB meetings. And anyway, I don't want to go into these details. But let me just say what I think, and what is much easier to use to explain the prompt GRB spectrum is the very photospheric emission that was dismissed from the beginning in the beginning of 90s. It was dismissed for the reason that it was supposed to be blackbody emission. And we obviously see no thermal spectrum. And so it was natural to think about something that emits an optically thin region and outside the photosphere, right? But in fact, it turns out if the jet is heated as it expands and as it's still opaque, that the spectrum that it releases actually is not thermal. And in fact, it is very close to what is observed. Let me just show just one simulation of that, just to make this point, and then we'll move on. So, okay, this is a sketch of what's happening with an opaque jet. There is a thermal emission carried by the jet, and there is a so-called wind zone when photons are not produced in sufficient number, maybe, and then there is no thermal part, which is still optically thick. This is where plasma is heated, and there is ongoing comptonization. And of course, many people talked, and see here's some list of papers. Many people actually prefer this kind of model, understanding that you can explain the MEV peak at least. And let me show one simulation that was done by Andrei, and I think it's still state of the art. It was done in 2016. And this simulation is basically a radiative transfer simulation. So you start with Planck radiation. You see Planck spectrum here at the beginning at a smaller radius. So this is the radius. This is optical depth at the beginning of the simulation. Planck spectrum, somewhere here. And then you let the jet expand while you keep heating it. And the heating is what some other communities might call is hybrid heating. It's thermal heating plus injection of non-thermal particles. And it's this kind of analogical model that you can just solve exactly by following all radiative processes of absorption, controlling double Compton scattering, reproduction, everything. So it's done using very detailed code of radiative transfer. And let's see how the spectrum evolves. As the optical depth drops, radius will grow. And you will see how the blackbody spectrum turns into something that is very close to what we usually, what many observers use to fit the GRB spectra with the band function, so-called smoothly broken parallel. So you can see how the peak is around MEV, and it kind of reflects the initial temperature, which is naturally 1 MeV at the center of the explosion, but it's modified as the jet expands, but not by a huge factor, so it stays around 1 MeV. And then you see spectrum, when the jet becomes optically thin, you see this escaping spectrum which can fit the data, which we actually did. And so these are two examples. We did for 3 GRBs. And we found, well, of course, one parameter that you need to assume, because some particles that inject will produce some synchrone radiation, which depends on the magnetization of the jet. So we found that to reproduce the spectra, so blue simulation, red band fit reported in the literature from the data. So if you use sigma, which is between 1% and 10%, and non-thermal heating is comparable to thermal, you explain the spectrum really well.
Yeah.
Okay.
Yeah. One question, Andrei. How sensitive is it to a non-thermal tail? Because when I played with this a long time ago, if you have too many non-thermal gamma rays, you can drop the temperature down to like 10 kV because you make a pair catastrophe. It's like a
you needed 10 kV because because you don't want 100 keV, because here it's all boosted by gamma.
Yeah.
So gamma, of course, from this fit we also find gamma, which is a few hundred. So if it's 10 keV in the jet frame, it's 1 MeV.
Okay.
In the observer frame. Yeah.
Yep.
What is the source of the non-thermal heating? If there are no acceleration of particles?
I'll talk about it next. Yeah. Yeah. This perfect. Yeah, it's a great question. Right. So you need synchrone, by the way, because you need to produce the right number of photons here, which is of course followed in the simulation. Okay. So how particles are accelerated? If I just said that the internal shocks don't accelerate particles, and it's related also to another issue that was discussed in many papers. This is the issue of possible TeV-PV neutrino production by shocks at very large optical depths. So here is another basic point that is maybe known by now, that that of course internal shocks actually are not quite collisionless shocks. If you so these are shocks which are mediated by radiation. So if you start with the profile of outflow, which has which is prone to shock formation, the steepening of the velocity profile that would eventually will lead to shock, the steepening will be stopped by radiation diffusion, by the force that comes from the gradient of the photon energy. And so that's why eventually the shock establishes a profile with length scale comparable to the photon free path for relativistic or relativistic shock. And so what's happening in these shocks, because they're so broad, plasma stays cold. It stays at constant temperature in the equilibrium with radiation, because the cooling time scale is so short. The time scale for the radiation, which completely dominates the heat capacity, by the way, of the jet, there are 10 to the 5, 10 to the 6 more photons than particles. So radiation controls the plasma temperature on long time scales, on radiation-mediated shock time scale. And the only thing that is happening in this shock is that photons gain energy, not particles, but photons, because photons bounce between upstream and downstream, and they experience a kind of Fermi mechanism this way. Okay, this is a first principle simulation. Well, it's radiative hydrodynamic simulation of how you start with the flow modulated with some sine, whatever, tangent profile, and you let it steepen, it launches a pair of shocks actually, and then you can follow how the shock develops. So I did this simulation a few years ago, and it shows that it is coupled to radiative transfer. So hydrodynamics, how the material moves is of course coupled to what the photons do, and you need to follow the photons individually. So it was done using, well, you could do it on a grid as well, but I did it individually using Monte Carlo technique, of course, including Klein-Eshim and everything. And so you can see here, I have to wait a little bit. There is a steady state structure, which is radiation-mediated shock, and you can see the initial spectrum upstream. This is unsuspecting plasma with some thermal radiation. Then, boom, that's what's happening with the radiation inside the shock, and then downstream it relaxes again to something more quasi-thermal, but hotter, according to the jump conditions. And I would like to make 2 points. This is not surprising, of course. This is what you would expect radiation-mediated shock. So 2 important points here are this: one, this spectrum extends for relativistic shock, or mild relativistic shock. Gamma beta of shock is greater than 1. There is a lot of photons, well, an interesting fraction of photons, about 10 to the minus 3 of total photon number, that end up above electron rest mass. And these photons immediately convert to electron positron pairs. It's only 10 to the minus 3 of the photon number, but it's 100 times more than the original proton number, because there are many more photons than protons. And so the plasma becomes dominated by electron and positron pairs. That's what's happening in these shocks. And so correspondingly, the length scale of the shock shrinks by a factor of 100. the thickness of the shock, because it's proportional to the free path. So that's one point. It's kind of funny. The other point, which is important for heating, for acceleration, could be important for acceleration, is that if you add magnetic field, that one can demonstrate that, in fact, there has to be a collisionless subshock in this radiation-mediated structure. Otherwise, you cannot satisfy jump conditions. And indeed, direct simulations did verify that you have this velocity profile that you find from the simulation. So in this collisionless subshock, which works on the plasma scale, particles are impulsively heated. Of course, you need significant magnetization. By significant, I mean sigma 0.01 to 0.1, 1 to 10%, which is typical that we think from photospheric models that I think sigma should be this observationally. So it's not so big, but it's big enough to completely quench Fermi acceleration of particles in this collisionless subshock. So the bottom line here is that subphotospheric shocks, they are mediated by radiation. They have a collisionless subshock that impulsively heats the plasma to basically electrons and positrons gain a fraction of the proton energy. This fraction is about 30%, and it's shared between all electrons and positrons that are available there. Depending on the pair loading factor, that controls the energy of injection. So this injection is not dramatically energetic. Particles, electrons, and positrons may be injected with Lorentz factors of a few tens here. So that's one source of injection of non-thermal particles below the photosphere that affects the emission that comes out from the photosphere, but it does not produce yet, of course, very energetic particles, no ultra-high energy cosmic rays or ultra-high energy neutrinos from here, nothing yet. Okay, but there is another aspect. I don't know how I'm doing on time. Wow. Okay. There is a rich, GRB physics is rich and interesting. So it's not reduced to the cartoon kind of pictures in terms of forward shocks. A robust fact that was realized first by Zhenya Deryshev, that neutrons, GRB jets have to carry neutrons. There must be free neutrons. And these neutrons are going to decouple from electron-proton plasma when the collision timescale, these are nuclear collisions between neutrons and protons, becomes longer than the jet expansion timescale. And because the collision cross-section, nuclear collision cross-section, is about 20 times smaller than the Thomson cross-section, this decoupling happens at about 1/20th of the photospheric radius, if you calculate it without including pairs. Okay, so the collision, these collisions which have become most dramatic. So before, as long as neutrons are coupled to the protons, they move together. There's not much dissipation. But as long as they begin to decouple, if there is a reason for them to have a difference in Lorentz factor, which could be, for example, and that's what was discussed by Deryshev et al. If there is still radiation pressure that is accelerating the electron ion component, and neutrons now decouple, and they kind of lag behind a little bit in velocity, and they create this friction condition when a lot of energy is dissipated. And so this dissipation has to happen just in the subphotospheric region at from about 1/20th, 1/30th of the photospheric radius. So there is a natural source of heat there. And I could also add here that actually any internal shock that happens in this region will sweep electron-proton plasma, but it will not quite sweep neutrons. And so you create configuration where neutrons penetrate with neutron fluid with some Lorentz factor from the upstream, penetrates into downstream, which moves with a different factor. And here you go. Here you have again this frictional situation when you have two component jet, and you go to have collisions between them. These collisions produce heat, and they inject non-thermal particles, as shown in the next slide, because they can be inelastic and they produce pions decay. And so you have injection of electrons and positrons with well-defined Lorentz factor of about 100, ratio of pion mass to the electron mass. And one more remark here is that if you think about these subphotospheric shocks, that actually they're not only radiation-mediated shocks with some collision-less subshock because of the non-zero magnetic field, but also they are mediated by neutrons on a larger scale. So neutrons also get scattered back and forth, and they shape the velocity profile on the largest scale of the shock. So there are three scales in the problem. There are two subshocks. There is a neutron shock, there is a radiation-mediated shock inside it, and there is a collision-less shock inside the radiation-mediated shock. That's the structure that has to be there. Okay. It still does not activate Fermi acceleration, but one possibility that appears here is the converter mechanism that Zhenya Yershev proposed, and a similar mechanism was discussed by Boris Stern at about the same time. And the idea basically is that neutron could, through scattering of collision with a proton or collision with a photon, can convert into proton, and then proton can convert to a neutron. So now you have the possibility for particles diffusing back and forth by changing neutral state to charged state, because neutral state doesn't care about the magnetic field in this argument that magnetic field kills acceleration does not apply to the neutral state. So Zhenya talked about this mechanism a few weeks ago, a month ago, so I'm not going to repeat this in detail. The problem here is that it's hard to find an injection mechanism into this mechanism for this converter, because in order to convert a proton to neutron, you need to collide the proton with an energetic photon with energy 100 MeV in the proton frame. And so you need sufficient energetic photons, but at large optical depths, or even at the photosphere, the high energy photons don't live long. They're killed by gamma-gamma absorption very quickly. And so you're missing targets. So you can only start this acceleration if you inject the proton or neutron with a high enough Lorentz factor. So it starts to interact with sub-MeV photons in the jet frame. And it's not easy to find this injection process. All right. Yeah, I mentioned that this is what inelastic collisions do for you. They create pions. Pions decay into muons, muons decay into electrons and positrons. And as a byproduct, you have neutrino emission with very well-defined energy. And this energy is between 10 and 100 GeV, detectable by ice-cube deep core. But there's not much attention to this among ice-cube people, I think. But I think most of the neutrino luminosity has to come out in this form of neutrinos, not high-energy neutrinos, simply because high-energy neutrinos require special conditions to get particles to high energies, which are not easily accessible in the GRB settings. But these kind of things have to happen, because even if you don't have neutrons, even if you just heat proton component to mild relativistic temperature, that's it. These protons will do collisions, and then they will be inelastic. Okay, and they will emit neutrinos. All right. Then electron distribution function that you expect, and that's what this kind of distribution function that fits from GRB data is basically a combination of thermal heating and non-thermal heating. This is the injection. This is pion rest mass if you have injection from inelastic nuclear collisions. And then they cool down. This is the fast cooling low energy part of the injected non-thermal electron positron spectrum. And then, of course, you have inverse Compton cascade. It's a high compactness, so you have secondary pair production here. And at the same time, you heat the thermal electron positron plasma because they experience Coulomb collisions with the hot protons. And these two processes are related to each other. And in fact, if you just do collisional heating, you end up with a spectrum which is pretty close to GRB spectrum. Okay, wow, I'm running late. Well, not surprisingly, but I'll probably skip some parts. So I was going to talk about magnetically dominated jets. Yeah?
Hey, Andrei, just don't worry. I think we have another half an hour, so maybe you could take 15 minutes from that, half an hour or so.
Okay. I'll try to do this faster than 1:15. Yeah. Okay, I'll just make some brief remarks about magnetically dominated jets. Magnetically dominated means that magnetic energy density exceeds rest mass, comparable to rest mass. Internal shocks do not easily work in these settings because they are Larmor mediated and there's not so much dissipation in these shocks. Basically, these shocks are in high sigma limit. These shocks are basically jumps in magnetic field. But you've got magnetic energy reservoir now, and you can release it by magnetic reconnection and turbulence. There are several papers. It's not as visible as shocks among GRB people, but still pretty well known. So I'm going to tell you just briefly what we've learned from first principle particle and cell simulations. This is recent work. Several groups have been working on magnetic turbulence and reconnection. So we're talking about turbulence here in magnetically dominated jets, so sigma 16 in this example. This is simulation done by Jonas Netela at Columbia. And so you will see color is JZ. Z is the Z-axis is a low magnetic field, J is the current, electric current. So you can see here, okay, I'm not going into detail, you can see turbulence. But if you look at it, actually, you will see formation of current sheets as well, and you see how it decays over time. So these kind of simulations allow you to start, and this is big box, like 2000 cube. So these are expensive simulations, but they are showing how the magnetic energy goes into particles. And so, so Jonas have done simulations with radiative cooling included, which is relevant for many settings, but including GRB jets when you have strong radiative cooling. And here is the main conclusion is that stochastic acceleration by turbulence is suppressed by radiative losses. And you have only impulsive acceleration that is that comes from current sheets forming in turbulence. It was discussed in particular by Luca and Lorenzo in recent work, also at Columbia. So there are several simulations now that all agree that basically what happens when you stir a turbulence aggressively enough, just perturbing magnetic and letting them relax, then you will have injection of particles, like impulsive heating of particles to the sigma E prime, which is sigma if you have electron positron plasma, is how much the simulation by the way I've shown is for electron positron plasma, but also there's more work now done on electron proton plasma. So if this sigma prime is high, then you can have impulsive acceleration to high enough Lorentz factor. Another interesting finding is that the heating is anisotropic. So particles are mostly heated along the magnetic field lines with pitch angles of 0.1. That of course affects the synchrone spectrum that you can see from turbulence, from this magnetically dominated turbulent jets. And you can estimate the peak energy. And then you can find that, of course, peak energy will scale as magnetic field times the sigma E prime. So it's sensitive to magnetization. So in principle, you can bring it to the right value if your sigma E is 10 to the 4. Then magnetic field, you know, from the jet power, this is mostly Poynting flux because it's dominated magnetically and it depends on radius. Magnetic field scales as 1 over radius in this expanding jet. But importantly, it also scales with sigma, it scales as sigma squared. So it's not easy to have a preferred energy in this model around 1 MeV.
Can I have a...
Yeah?
I mean, I never understood how it works because I looked at your papers, not yours, but you need a radius of 10 to the 15. But you need relativistic turbulence. So you need the jet to be still highly magnetized with a bulk Lorentz factor of 100.
Yeah.
And to be beyond the photosphere. In this region, the jet is already acausal, you know, it's expanding conically. So I don't see any reason why you will get turbulence there, dissipation.
Yeah,
If it's likely to occur, it's likely to occur inside the star. And that won't help you much because it's...
That's right. I mean, of course, there is always an issue whether you develop turbulence at the radii you want it, because you want radii here certainly outside 10 to the 15th, also actually outside 10 to the 16th, because otherwise you start to produce many pairs and it's a headache for the spectrum. So you want large radii, and indeed it's a good question. Yeah, I mean, I can refer you as one. We didn't discuss that at all. And like I'm telling you, it's not my preferred model actually for GRBs. I don't think it can explain the observed prompt radiation spectrum or variability. But so Chris Thompson had a few papers where he argued that you know, he had a complicated picture of how turbulence and magnetic dissipation could be triggered by the external shock by interaction with the stellar wind. Maybe that would be helpful, but okay. I don't want to go into too much detail here. And I agree with you, it's not clear if you naturally expect it to happen. Another topic here is radiative reconnection. Again, reconnection, there are many particle and cell simulations by now, and several for radiative reconnection, meaning that you include strong radiative cooling of particles, particularly by inverse Compton, but also synchrone you can include. But for most simulations, just impose some cooling energy density, and cooling goes as gamma squared Lorentz factor squared. And so what the basic feature of all these simulations is that plasma is cooled, is trapped into heavy plasmoids, and these plasmoids, which may contain, by the way, hot protons, are dragged by magnetic stresses, and they in a lot of most of 80% of 75% of energy of the of magnetic reconnection released by magnetic reconnection goes into dragging these cooled plasmoid by magnetic stresses, so rather than to individual particles. At any rate, when you look at the particle distributions that you form from magnetic reconnection from all the big simulations, I don't think there is any hope for them to fit GRB spectra. It's not been explored until, but just look at this. They're broad, they don't have a preferred peak and preferred position.
Andrei, if it happens inside the photosphere, though, the details, the spectrum are pretty insensitive to the acceleration spectrum. Like if you take hybrid models and change the spectrum, it just
That's true. That's true.
Average energy.
That's true. So that's why the injection, as long as your injection Lorentz factor is, you know, a few tenths or above, it doesn't matter, because you have inverse Compton cascade and it's all reprocessed into pairs, and that's it. You only care about total energy that is that you inject. Yes, and that's why I think that internal shocks can work as well with the subshock, where you have impulsive heating, could work as well as nuclear collisions that produce points that decay. But for magnetic reconnection, it's a different problem in turbulence. I think it's just overall distribution that you form. It's not even impulsive, really, heating. It's overall distribution that we get. But it's a good point. Yeah, sorry, go ahead.
A related question, what about models where there's a preferred magnetic orientation, like striped jet models by Spruitt? So there the reconnection could occur because the field is organized, but you have current sheets and things like that. So you don't need the turbulence as much to do it?
You don't need. So yeah, so I listed this work, including among others, but I didn't discuss it in detail. Yeah, you don't need turbulence. Actually, reconnection, I think the best, in my mind at least, I think the best way to formulate it is like this. Reconnection can accelerate particles with very broad distribution. And sometimes it's part of turbulence. And then turbulence also does it successfully, even despite radiative cooling. Because otherwise turbulence, if you have, we also did, Jonas did simulations when you have more peaceful turbulence, which does not trigger current sheet formation, tearing instability of the current sheet at next points. So it's not triggered this process. You don't have injection. And you don't have stochastic acceleration, and you just end up with a thermal heating from turbulence. But when you have magnetic reconnection appearing in turbulence, then it can produce interesting non-thermal particles. But my point is that it's not easy to see why these non-thermal particles would have anything to do with what we need in GRBs. But maybe I'm wrong. I mean, this has not been checked carefully.
Yeah.
Okay. So
Thanks.
yeah, you have another question?
No. Thank you. Thanks.
All right, great. So another basic point about GRB jets, they have to be, I mean, any dissipation mechanism that I've talked about, it produces pairs. Okay. Almost virtually, I mean, yeah, you can have subrelativistic shock, then it wouldn't radiation mediated shock, but otherwise, with a subshock, it already would produce pairs. So I think it's fair to say that, of course, if you have magnetically dominated jets, all your plasmas will be mostly pairs. I mean, you have some ions, but the energy that you release quickly is thermal cascades turns into pairs. So it's a general situation, a quite general situation, that GRB jets are filled with pairs, and they freeze out later, even if you stop dissipation, and they freeze out with non-trivial pair fraction exceeding 10. For example, I calculate this for nuclear collisional heating as an example, and you end up with numbers like above 10 for this Z plus minus, 10 times more pairs than ions. And the rest of my talk, yeah.
Where it comes from this ratio 10? More than 10?
Yeah, it's a combination of 8/3 that you have an annihilation rate and the heating strength for nuclear collisions in particular. It's well-defined heating profile. It goes down with radius because density, this is two-body collision process. So density goes down, the collisional heating, inelastic collision rate decreases with the radius. And in the end, you end up, when you calculate it, you end up with this number. So think of it as something that is like 1, but not quite 1, or like 10. Okay. So the rest of my talk I would like to spend on external blast wave, which is also interesting. And I would like to highlight basic point, which I think some of you heard from me 10 years ago, maybe, or 5 years ago. And also like to show some new results that were which are related to particle acceleration. So external blast wave is also pair loaded at radii smaller than about 10 to the 17th centimeters. And this is well known, well, I don't know how widely it's known, but it's established that when you have gamma ray radiation passing through any medium, doesn't matter what is the density of the medium, every particle gets dressed into electron-positron pairs because some gamma rays, a small fraction of them, basically think of one electron which is exposed to flux of gamma rays, and it scatters one of the gamma rays, let's say, to significant angle from the initial nearly perfect collimation. And then the scattered gamma ray immediately collides with the primary gamma ray, which is collimated, and turns into a pair. Not immediately, but soon enough, if you are at enough close radius. And by enough, I mean less than 10 to the 17th centimeters. So it's not a small radius. As a result, so you see here the gamma ray front, this is from GRB, then there is this swept up external material, and you see the ejector that is driving all that. And this is zoom out of this, zoom in of this region. So you can see schematically how this medium should be filled with pairs. I would like also to show you a simulation. It's not a model, really. It's not in the GRB sense, because sometimes people talk about models, and what they mean is a speculation. This is a fact. If you have gamma ray beam going through plasma, the plasma is going to be enriched in electron-positron pairs. It's just scattering followed by absorption. It's first principle calculation. And you can do this carefully by taking whatever gamma ray beam you like. You can take the observed gamma ray emission, for example, in this case, this one famous burst of 80916C, which had a GV counterpart, the first one, I think, really bright one. And so just take this gamma ray spectrum and shine through one particle, test particle. Every other particle in the ambient medium will do the same when it gets exposed to the gamma rays. So here, let's pick a particle at this radius, 1.5 times 10 to the 16 centimeters. And let me launch the simulation. So you see, this is the gamma ray front. There are many gamma rays. So, and they're moving, they're perfectly collimated, moving toward this particle, this continuous pink. Once they reach the particle, some of the gamma rays will start to scatter. And the scattered gamma rays will be shown by red dots. They're going to move. And some of these red dots will convert to a pair. And a pair is a black circle here. So it's a complete detailed Monte Carlo simulation for this particular gamma ray. And you can see that the pairs that you create, they do the same, right? They scatter more photons, these photons. So you have an avalanche of pair creation. Okay, this scary guy is the forward shock, because after the prompt gamma emission, of course, there is a blast wave. And the forward shock is going to pick up all that stuff. You see here Z, this is the pair enrichment factor, which is going already 500. And also you see this particle begins to move because all these pairs together with this particle, they are pushed by the radiation pressure and they're gaining velocity. So beta already 0.7. So the shock has to chase the particle. Eventually, of course, it will win. The shock will collect all that, the particle and all that stuff that has been created. The point that in the end, by the time it collects it, the pair enrichment factor at this radius, 1.5 times 10 to the 16 centimeters, is 1,000. Okay, so you have 1,000 times more particles than you would naively think in the ambient medium. Effectively, the shock interacts with external medium, which is enriched at this radius by in pairs by a factor of 1,000. You can calculate, of course, this enrichment factor as a function of radius at all radius, not just that radius. I just told you this one right here is about 1,000. But here is how it depends on, for this particular GRB spectrum, this is how this enrichment factor depends on radius. And you can see that it drops to 1 outside 10 to the 17th centimeters. And it's pretty good approximation depending on the exact spectrum of the burst, but it's a good approximation. For bright bursts, you have 10 to the 17th pair loading factor. All right. So as the blast wave picks up that pair-rich material, and again, it's not a fantasy. It has to happen, right? The blast wave has to pick up all this stuff, and it shocks it. It interacts with very rich pair-enriched material, and therefore its emission will evolve very quickly with radius and with time, simply because the Z plus minus pair enrichment factor is a sensitive function of radius. So the blast wave will first pick up stuff which is very rich in pairs, and in the end it will start to interact with normal plasma outside 10 to 17. There is a well-defined emission signature associated with this pair enrichment effect. And because this characteristic radius depends only on the observed energy of the burst, it's like a ruler. If you see this radiative effect that I'm going to talk about in a second, associated with this pair loading radius, and you measure the time at which this effect happens, that's it. You would know the radius of the blast wave at that time, and you would know its Lorentz factor. Okay, so it's a robust way of introducing a rule of measuring radius of a blast wave if you find radiative signature of that. Now, radiative signature is not going to be small, like I said, because the basic proposition here is that early afterglow, early gamma ray afterglow is nothing else but the inverse Compton scattering of prompt radiation by the shock-heated material. Here, maybe I should pause a little bit because, right, so you need to think about it. So what I'm saying is that the blast wave is immersed in prompt radiation for many bursts at early times, at early enough times. It takes time for the final duration gamma ray front to completely get out and overtake the forward shock. It takes time. So it happens that for this radio of interest, the post-shock material is still bathed in the prompt radiation, okay? And which has huge energy density and which cools effectively this shock-heated material. All right, so it's it turns out that when you look at GeV the early high energy gamma ray, which is GeV. For TV, we only have late data. So the GeV peaks that we see of GeV afterglows, the peak typically, and maybe actually exclusively, before the end of the prompt emission. When you look at the recent paper by Fermi lat analysis, they have actually plot showing that the peak of the, when you correct for observational bias effects, it turns out that the vast majority, maybe all of the GeV peaks, it happened before the end of the prompt emission, which means that we deal with radiation. The source of that radiation was exposed to the prompt emission. And so the key point that I want to make here is that, which I made several years ago, is that the GeV flash is nothing else but the inverse Compton scattering. Inverse Compton emission that comes from scattering of prompt radiation by the forward shock. All right. Now, another thing that you can conclude from this plot is that this GeV flash peaks well before the blast wave begins to decelerate, because the deceleration time is not before the end of the prompt emission. You have to, if you think of it, you need to work really hard to design a model where the prompt emission will get out before. So you would have to, basically what this slide curve is telling you is that the peak of GeV emission is not shaped by the deceleration of the blast wave, it's shaped by something else. And so what I'm saying here is that it's shaped by the Z plus minus drop factor. All right. And in particular, you can show that the peak of the GeV, the best way to say that, when Z plus minus is larger than 10 to the 4, the energy per particle is so low that you cannot produce GeV emission, right? So the blast wave shares its energy with so many pairs, energy per particle is so low that its inverse Compton scattering doesn't reach the GeV band. And therefore there is a delay. You have to wait until the blast wave gets out of this very pair-rich domain and starts to sweep lower Z plus minus stuff. And then you can get inverse Compton emission. That's why you have the delay. Okay, that's the idea. It's just another example, but of course, it's not just an idea. We have calculated this back in 2014, and it was another paper in great detail. And by solving basically this problem, you launch a blast wave, you have prompt emission, you take it from observation, this prompt emission is duration, spectrum. And the key point here is that in agreement with the plasma physics that we know about shocks, the emission from this blast wave is dominated by thermal plasma. Inverse Compton is dominated by thermal plasma because most of the energy goes to thermal, and it interacts easiest with Thomson cross-section with the prompt emission. And so then you don't have any other parameters in the problem, right? You have only one, essentially one parameter, you know, energy from observations. You have only the external density parameter. You don't need this epsilon E and epsilon B. Epsilon E, you neglect no thermal component. Just say, okay, it's Maxwellian. I know how much goes to electrons from peak simulations, 30%. And that's it. You have only external density, single parameter. Let me show what you get from this. You can do full Monte Carlo simulation. So we did that. Basically taking particle here, let it be overtaken by prompt gamma rays, then be overtaken by the shock wave and heat it impulsively, and then continue to upscatter photons. And collecting all its inverse Compton photons and the pairs that they may create and the emission from those pairs. So collecting all that stuff and calculating the arrival time of those photons. So it's a first principle calculation, which gives you this light curve. All right. And like I told you, there's one parameter. In this one parameter, you would expect it for Wolf-Rayet progenitor wind to be 10 to the 11th gram of that order, with huge uncertainty factor of 3 maybe, or 5, or 10 maybe even. But the point here is that we did find that a good fit to the data with precisely this kind of parameter. And there are nothing else here to basically to play with. So it's basically a single prime to model, if you like. Okay, so this is spectral evolution. All right, so I should finish. So I'll just show you TV predictions and GV predictions for other bursts. So we analyzed 7 bursts in follow-up paper. Again, fitting them with just the same model. Again, single prime to model. Pretty good. TV, of course, was not observed at the time. You can see it is delayed. TV comes up later because you need to, you need to wait until Z plus minus drops, energy to particle rises, and you have inverse Compton in the TV band. So these are 2 last bursts I wanted to show. You see GV data here, GV data here. And these 2 bursts also had optical data. You can add only one more parameter, epsilon B now, magnetic field, essentially parameter, and say, okay, I have the same particles, nothing else, no non-thermal tail, nothing else. I have the same particle, but let them also produce synchrone emission. They produce inverse Compton, it's shown here. It's been fitted. But let me just add epsilon B and see what will be the synchrone emission accompanying that burst and compare it with the data. So when I saw this first time, I thought that's it, my job is done. And actually that's what I did. I stopped working on it. And it's surprising that sometimes it looks like it's not everyone knows that. But this, if you count how many parameters you would need to fit this kind of light curve, I think you would count it, probably 7 phonological. So this burst, these 2 bursts, they reproduce simultaneously GV flash, early flash, and optical data. And I think that's it. It basically proved that it works well. Also, with the 7 bursts, you look at a parameter, and in all of them, it turns out about varying around 10 to the 11th. So I think in all cases, we deal with the Wolf-Rayet wind in these GRBs. One of them was classified as short, by the way, but again, it's a separate discussion. Like I told you, you from the radiative signature, you know this pair loading radius, it's a ruler. Then you know gamma, arrival time, radius, you know gamma. So we found gamma, and it nicely extends the correlation that was obtained before from the optical peak arrival times in those cases where it was measured. Okay, do I have okay, 4 more minutes? I promised but I just 3 or 4 minutes. I have, I think, exactly 3 slides. I would like to show the results that are unpublished. This is tour de force, really, work by Daniel Grussin, who's working at Columbia. And this is related to the stuff that I talked about. The question that Daniel studied is how the shocks that propagate in pair-enriched plasma differ from normal electron ion shocks. These are the shocks that we deal with in early afterglow. And so he did a set of big simulations with different pair loading factors, different magnetizations, and the shock clearance factor 50. Let me just show 2 slides literally. So this is sigma 10 to the minus 5, upper panel, no pair loading. Here is ion density, you see filaments, this is normal Weibel shock. Low sigma, Weibel shock, very good. As you increase increase Z plus minus, you can see the shock eventually transitions to suppressed Weibel turbulence. And as I will show next also, it's like that. It does not accelerate particles. It's for this sigma. So this let me formulate this way. So this critical sigma which was known to be 3 times 10 to the minus 5 for pair free shocks has now changed. It's dropped with increasing Z plus minus to significantly low value. So these shocks are really Larmor mediated with high Z plus minus rather than Weibel mediated. And otherwise, the shock, the simple result is that these pair loaded shocks in early afterglow, they inject energy into ions and comparable energy into electron and positrons, and they share democratically with energy, basically. Right, that's the simple result. Independent of Z plus minus, the energy budget for pairs is the same. That means that energy per particle goes down as 1 over Z plus minus. Very simple result, now confirmed with simulations. And finally, I'll stop there. So is there any Fermi acceleration? And the answer is, with increasing z plus minus, no. For ions, there is zero Fermi acceleration because, well, more precisely, this critical sigma scales as 1 over z plus minus to the 4th. So we have interesting pair loading factor, and we have huge pair loading factors in GRBs. They stop accelerating ions altogether. And this is first principle peak simulations that show that electrons are still accelerated, but not to the energies exceeding the ion energy. Since ions are not accelerated at all, that puts a big limit on the electron acceleration too. And this is just, and this last slide, it's how you see changes in the spectrum of ions and electrons as you change z plus minus from 0 to 12. These are ions, you see no thermal tail developing and keep progressing with time. And here with time, you see it's disappearing. So whatever in the initial perturbation during shock formation, it's gone and you see thermal ions. For electrons, you see something, but it's limited. I'll skip ultra high energy cosmic rays. I had some comments, but like I anticipated that I will fail to talk about everything. So here's my summary, and I should stop. You can read the summary. Thank you.
Okay.
Well, I put you to sleep, I guess, guys. So
thanks very much. No, I don't think you put anyone to sleep. I think it's extremely interesting. I'm sure there are some questions. Zhenya.
Yes. Coming back to the very beginning of your talk.
Go to the very beginning.
When you described the model, no, almost the beginning.
Okay.
When you describe the model of photospheric comptonization, you need sigma, which is, say, less than 0.1. On the other hand, if you have magnetically launched jet, then before this point, you have a situation when sigma is larger than unity. Does it mean that you do not consider a possibility to merge these two models together in a single model, or do you have a way to go from sigma, which is larger than unity, to sigma 0.1 and produce radiation while sigma is 0.1?
Yeah. Okay. It's a good, I guess you're basically asking, well, if we try to do the same radiative transfer, but keep increasing sigma, would we get any good results with high sigma? We actually didn't study very high sigma. But sigma above 0.1 were not so good. Between 0.1 and 1, like 0.5, they're not good. I think Andrei tried sigma up to for 1. Yeah. So we didn't quite, because physics also.
Okay, then it's even worse. I mean, you have even longer way to go.
To very high sigma, you mean?
Yes, if you have very high sigma at the beginning, then how does it expected to work? Or you simply say that high sigma is not suitable for this kind of models.
So this simulation is done with sigma as a parameter. This is transfer simulation, right? So we just said, let's assume a given sigma in the jet. And it's orthogonal. Yeah. And let's try to fit against the data and find what sigma would fit the data. And we find that you can look at the paper, 3 bursts in the sigma f in this range for the fits. That was the take of this analysis, like pure phonological point of view. And then later I started to discuss what physics, what kind of, but I actually didn't discuss what controls sigma. And it's another interesting topic. This is more MHD.
Wait. Andrei, I'm sorry, but I think that I probably wasn't too clear saying the question. The question is, if the jet is magnetically dominated, then of course the magnetic energy can dissipate somehow, but the most energy input to the particles will be when sigma is large. On the other hand, when you model emission, you need sigma which is not large. Is there a way to make the delay between energization of particles and emission of particles?
But here the
Or
source
you
of
simply
energy,
say that high sigma is not good for this model? And
right,
that's it.
but the source of energy here is not sigma, it's not magnetic field.
What is sigma then?
Sigma is just a parameter that is telling you the value of the magnetic field that controls the synchrone emission from the particle.
Okay, then it's a magnetic field.
It's not magnetically fed. No, it's just for example, it could be
yes. But can you feed the spectra if sigma is large at the beginning? This is the essence of the question, or not?
We didn't try an evolving sigma, and it's a good question. Maybe you actually do expect sigma to be large in the beginning and drop later. But actually, so we tried already fixed sigma, the jet which carries fixed magnetic field. But when you look at MHD models that may be used to predict how sigma evolves, they can start with high sigma, then they can have kink instability and this magnetic dissipation at the time when the jet tried to break out from the star, like through the it's going through the nozzle. This is a topic I didn't touch in my talk. But this typically at much higher optical depths than the simulation that we ran here, which started at optical depths of 1,000. I think this nozzle can be at higher optical depths than that. So maybe most of the magnetic dissipation that reduced sigma to this level happened at yet smaller radius with even higher optical depth. And then sigma stayed approximately constant. Maybe that's, I guess.
Yeah. Okay, I see. Thank you.
Udi Nakar?
Yes. Just one comment. Well, I have a question, but first a comment about dissipation of the magnetic field. It's very plausible. There's a magnetic field, even if you start with a high sigma jet, that it will be dissipated at relatively small radius, deep in the star, much lower radius than what you need here for the radiation. It's actually quite likely. But my question is, all the peak simulations that you show here are first principle, but you cannot include the back reaction of the accelerated particle on the upstream, which can generate magnetic field on large scale, for example, with Bell instability. So it's not clear to me how can we take these, the results of this simulation directly all the way to the observations.
Okay, so my comment.
If you can comment on that.
Right, so my comment would be this. If once you start the acceleration of particles, once you have Fermi process, you need to start it. Then, of course, the simulations are incomplete because it will keep going and you will probe larger and larger scales as particles gain high and high energies because it will be harder and harder to reverse them. It will take longer and longer time. They will go further upstream. It's true. But the points I was making is not about the final outcome of this Fermi-initiated acceleration, but whether it starts at all. And I think the answer to this question is robust because you need this kind of injection in this process, which is precisely controlled on that scale. This is why these peak simulations, I think, were designed in the first place. They wanted to see how particles would start engaging in this Fermi process. If they not started, then that's it. You know, just thermal plasma.
Yeah, but this can, for example, such feedback can increase significantly the highest energy you can gain, for example, in the external shock or something like that. So the first PEV that you...
the PV is order of magnitude number.
Yeah, but it can be even orders of magnitude higher if this back reaction increases the magnetic field.
If the shock becomes,
for example, you're getting out of the scale, which is,
yeah, there may be funny things indeed. The Fermi, it's very hard to simulate all this process through because the plasma simulations are limited in scale. Yeah, it's true.
Thanks.
Anatoly?
Andrei, I wanted to come back to what Udi asked earlier. For the internal shocks, the gammas are of kind of small. So you could get by with, I mean, we see in gamma of 2 simulations, for example, quasi-parallel shocks do accelerate quite nicely. Quasi-parallel means angle smaller than 45 degrees or so. So how what's the problem again with the internal shocks?
If you look at oblique shocks, in particular collimation shocks, there are things like that would be possible. But if you look at shocks which are farther out, where the jet has expanded, especially if we talk about this standard assumption that we observe, old assumption that prompt emission is the synchrone emission from optically thin shocks. That is happening outside the photosphere. These are big radii, 10 to the 14, 10 to the 13 at least, depending on velocity and gamma. And so these rays are so much bigger than the central engine and the progenitor that there the magnetic field was just advected out and should have become transverse because it's frozen into plasma. Unless you start, if you want to combine several things together, if you want magnetic turbulence.
Exactly, right.
Yeah, and then start to, but it's not what was, the turbulence itself will start to do something to the plasma, it will preheat it.
But is there another argument if internal shocks did accelerate particles, is there something else that would be violated in explaining the observations? Or, I mean, are they ruled out on basic physics principle, or are they ruled out by some other observation that you...
So I know that some people would disagree with me, people who like synchrone model. I believe that synchrone spectrum has no way of feeding the data because it, for some bursts it works. First of all, it would only be slow cooling or marginally slow cooling. And fast cooling spectra are just not working. Fast cooling synchrone spectra just not fitting the data at all. I think even those people who would like to use synchrone would agree with that. But they try to play with, like Michael Burgess, for example, an observer. He fitted a significant fraction of GRBs with slow cooling model. But fast cooling are just not working. Even with single value of magnetic field, I keep repeating the same argument some years. You do ideal electron injection spectrum with a cutoff, you do single value magnetic field, single value Lorentz factor. Even in that case, the synchrone spectrum that you get may be too broad.
Thanks.
Maxim?
Hi, I have a comment and question in the same time. It's in your case, you have more or less spherically symmetric shocks. And you can explain a prompt emission like some kind of comptonization of thermal emission, and here you will have somehow acceleration on oblique photosphere, like comptonization on different Lorentz factors flow. Can you comment it?
I'm not
Do
sure.
you understand what I mean?
Yeah, I'm not sure. So one
again, photosphere in a GRB has not a flat shape. It's quite deep inside of a jet and goes away for big angles.
We only see an angle of about 1 over gamma. Where gamma is the Lorentz factor of the jet. I think on that scale, it's relatively safe, maybe not for all GRBs, to say that we are looking at a small part of the jet. The jet opening angle is almost definitely larger than 1 over gamma, which is like 1/100 or 1 over several hundred. Another comment is that so it's effectively like part of spherical symmetric explosion. Another comment is the photosphere is not a surface, of course, right? It's very fuzzy. It extends over more than a decade, actually, if you look at it. So I'm not sure. I don't know if since I didn't get your questions quite, but maybe these two comments are helpful. Or maybe you can refine your question.
It's what you will see, you will see somehow like a quite oblique photosphere to direction of motion.
If what? In which
Technically,
case?
in any case, so when you have photosphere of a jet, if you just like put shape of photosphere.
If you look off axis, a little bit off axis.
Yes, in 2D.
You would need to go significantly far from the axis. You need to go over theta, which is the pole angle more than 1 over gamma, or comparable to 1 over gamma. Sorry, 1 over gamma. 1 over, sorry, you need to go over the angle which is comparable to the opening angle, which is much bigger than the visible zone, which is 1 over gamma.
In this case, you can contradict yourself. You have your visible angle is very narrow.
Yeah.
And if you, for example, like you are on 1 degree from axis, you already will have a quite strong angle dependence.
If the open angle, okay, if the open angle is 10 degrees, and you are looking at 1 degree.
Yes.
You would not know about the edge.
No, you will know. You don't know about like age, but like shape of your photosphere. It's not perpendicular to your motion. It will be.
I think it's okay to think of it as a piece of a sphere, of a spherical explosion. I mean, it's not a surface, but it's a region, and it's a locally quasi-spherical explosion. What's happening in this region has no way of knowing about what's happening near the edge. They're not causally connected. It's part of it behaves like a part of a spherical explosion.
I mean, you can have a strong shear inside of this region.
Okay, maybe, yeah, I'm not sure. I think it's okay to have spherical explosion and to think of emission as long as you view, if your viewing angle is well inside the beaming angle of the jet, which may be 5 degrees or 10 degrees or something, or 3 degrees at least. I think it's okay to think about it as a spherical explosion. We can discuss it later. I don't know if now it's a good time because it's already 4:31. For you, sorry guys, that's not for me.
Okay, maybe some final questions or comments. Andrew Taylor.
Thanks. Just a clarification, maybe. You mentioned that perhaps towards the end of your talk, you were modeling GRB 130427A Fermi emission, and that was sort of, it was quite quickly touched on, so I thought you could clarify on something. Were you saying that all of this GeV emission that was observed by Fermi you thought was inverse Compton in origin? Is that the take you were having?
Yes, this blue stripe, which is the model.
Yeah. So
is a very simple model. It's a black wave getting through the wind and emitting inverse Compton emission from the thermal plasma behind the shock. That's it.
Yeah, I mean, this is the brightest ever GRB seen by Fermi. And it was very well covered multi-wavelength data, you know, from X-ray, even some sort of even with New Star. And there was never any evidence for a sort of onset of an inverse Compton. So I was wondering, you're very convinced it's inverse Compton, this emission.
Well, I don't know, you see the fit. And that's, again, the wind parameter is what it should be for Wolf-Rayet star to do this. And you see the optical data, it's the same particles that produce inverse Compton at the same time they emit this optical data.
Okay, maybe rephrase my question then. At what energy would you expect some sort of dip feature to have occurred between the lower energy synchrotron and the high energy inverse Compton?
Yeah. Oh, I think there is another okay, I think I'm getting your question. I think there is another component which contributes in X-rays, and you can actually see it in the optical. You see here, you see this, like here it's a good fit, but here it's not. You see clearly a break, something else pops out.
Yeah.
Maybe later it comes to, again, but there is a component which is not accounted by that.
Okay, that's basically my question. Thanks.
Okay, maybe we should, so our chair should leave So I just continue. So thanks again to our speaker, very nice talk, very comprehensive discussion. And I just want to say that we didn't yet decide, but we plan to have one kind of session when we'll discuss all these GRB talks and summarize in overall, so we'll have a chance again to return to this question. So by now it's just again to thank the speaker, to participants, and I don't know if Reshmi is here or not, probably, but we will have in 2 weeks another very exciting talk by Brian Metzger. So thanks, Andrei.
Yeah, thank you. Thank you, Andrei. That was really great. And please send me your slides so that we can post it. Send me Thank you. Bye, everyone.
Bye.
Bye. Bye.
Bye.